satellite of mass m is in an elliptical orbit around the Earth, which has mass me and radius re. The orbit varies from closest approach of A at point A to maximum distance of B from the center of the Earth at point B. At point A, the speed of the satellite is v0. Assume that the gravitational potential energy Ug equals 0 when masses are an infinite distance apart. Express your answers in terms of A, B, M, ME, RE, V0, and G. And we actually have a variety of topics covered in this problem, such as gravitation, circular motion, rotation and conservation of energy, conservation of momentum, and calculus. Part A. Write the appropriate definite integral, including limits, that can be evaluated to show that the potential energy of the satellite when it is a distance r from the center of the Earth is given by Ug equals negative GMEM over r. So we're looking for the definite integral with its limit, that's already highlighted, and the potential energy of the satellite. The main goal of this part of the problem is to find the relationship between potential energy and an integral. And according to our equation sheet, we should know that F is the same as the derivative of potential energy with respect to dr. So that means that potential energy is the same as the integral of force times dr. In our case, the force is equal to the force of gravity, which is equal to Gm1 m2 all over r squared. And if we plug in our variables, we've got me and m to plug in. Putting these two parts together, we get that Ug is equal to the integral of g times me times m all over r squared times a little dr. The problem actually tells us our limits, since they state Ug at an infinite distance is equal to 0, which gives us the integral from infinity to r of g times mem over r squared times d little r is equal to Ug. Factoring out our constants, we're left with the integral of 1 over r squared times dr. And as we begin to solve through the rest of the integral, we're going to end up with negative Gmem over r minus a negative Gme over m all over infinity, which actually heads towards 0. So then we get our final answer of Ug is equal to negative Gme times m all over r. And now we have the AP point breakdown for this problem. We've got 1 point for the relationship between potential energy and force, 1 point for the integral, and then 1 point for the correct limits on the integral. You see, you don't actually need this part of the problem right, but it helps. And now on to part B, which is determine the total energy of the satellite when it is at point A. So we're looking for the total energy. Alright, so for part B, the main information that we're going to need to know is what total energy is, which is potential and kinetic energy. For the sake of our problem, potential energy is the same as Ug, which is nice, because you already have that answer, and then kinetic energy is equal to, like always, 1/2 mv squared. So using our information from part A, it stands that total energy is equal to negative Gmem all over r plus 1/2 mv squared. And then we have our variables to plug in, where r is equal to a and v is equal to v0. So rewriting all of that, we get total energy is equal to negative Gmem all over a plus 1/2 mv0 squared. And believe it or not, that's all of part B. So since we have our answer, let's look at the point distribution. So there are 2 points in this part, with 1 point for the correct expression of kinetic energy using V0, and then we've got 1 point for the correct expression of potential energy using A. And now we'll move on to part C, which may sound a little confusing, but is actually really easy if you remember the right equation. So, part C. What is the magnitude of the angular momentum of the satellite about the center of the Earth when it is at point A? So the main thing we didn't know And just as a reminder, point A is on the right-hand side, closer to the Earth. So the equation for angular momentum is L is equal to I omega, I being moment of inertia and omega being angular velocity. In our equation, we can substitute I equals mr squared and omega equals v over r, which will make our life a lot easier, as you can see, because one of the r's will cancel out, and we'll be left with L equals mrv. And our last step is to substitute our variables, with our velocity being v naught and our radius being a. So our final answer is going to be L equals m v naught a. Simple. And as for the point distribution, we get 1 point for the correct angular momentum expression and 1 point for substituting our variables. And on to part D. So D, determine the velocity of the satellite as it passes point B in its orbit. And that would be the point which is further away from the Earth, on the left. There are actually two ways to solve this step, and I will show you both of them, starting with the easier way. So, they're testing the concept of conservation of momentum right now, so they want you to note that the angular momentum at both points A and B is going to be equal, which means that m v naught a is going to be equal m v of b. And we can cancel out the m's, which means that v naught a is going to be equal to the velocity of b times b, which gives us the velocity at point B is equal to v naught a over b. 1 point is given for the indication of conservation of angular momentum, then we have 1 point for correctly substituting the velocities in radii, and 1 point for the correct solution. Now for the harder method, which I actually did my first time solving this problem as well. So, goes to show, just because it takes longer doesn't mean it's going to be that much harder. So I started off with using conservation of energy, meaning that the energy at point A and points B should be equal, and energy total is equal to potential energy plus kinetic energy, so both points have both a potential and a kinetic energy. So then the first part of this long equation is the total energy at point A, which we already got in part B, which is equal to mv naught squared over 2 minus g m all over A, and all of that is going to be equal to m times the velocity at point B squared all over 2 minus g m all over B. So since we're looking for the velocity at point B, in this method we're going to once again isolate the quantity VB. So I started by moving the potential energy at point B over to the left-hand side, and then I began to factor things out, such as the constants of potential energy, which are the same for both, G, M, which left 1 over B minus 1 over A in parentheses, which is still set equal to mvb squared all over 2, and the next step was to cancel out the m's. And I'd like to apologize for not crossing out with the marker the m and the potential energies put together, and that should be crossed out soon, but basically we're going to be left with v naught squared plus 2g me times 1 over b minus 1 over a is equal to vb squared. And when we take the square root of both sides, we're going to end up with the velocity at point B is equal to the square root of v naught squared plus 2g me times 1 over b minus 1 over a. And for the point distribution, there's 1 point for any indication of conservation of energy, 1 point for correctly substituting the radii and the velocities, and then 1 point for the correct answer. On to part E. And now we're actually going to have a different situation. We're going to be looking at the bottom picture. So, as the satellite passes point A, a rocket engine on the satellite is fired so that its orbit is changed to a circular orbit of radius A about the center of the Earth. And E would like us to determine the speed of the satellite for this circular orbit. And remember, circular orbit means we can use circular motion equations now. Probably the easiest way to start this problem is using the relationship of A is equal to F net over M. Since it is a circular orbit, we know that A is equal to V squared over R, which means that v squared over r is equal to f net over m, and f net in this problem is the same as fg, so v squared over r is equal to fg over m. We then multiply both sides by m, leaving us with fg is equal to mv squared over r, so that we can write out g times me times m all over r squared is equal to mv squared over r. This part is asking us for the speeds, so we're going to isolate the quantity v squared, which is going to give us g me m times r all over m r squared, and we can cancel out some variables like the top r and both of the little m's, which gives us v squared is equal to g me all over r, and we take the square root of that, which gives us v equals g me all over r, and we need to remember to substitute a for r, which is going to give us our final answer of v equals the square root of g me over a. So now for the point distribution. So we get 1 point for any expression of Newton's third law, F equals ma, and then we get 1 point for the correct centripetal acceleration and 1 point for our solution. And now for part F, our final part of the problem, which is determine the work done by the rocket engine to effect this change. For this part of the problem, the most important thing that we need to know is the work energy theorem, which basically means that work is equal to the change in kinetic energy, which is kinetic energy final minus kinetic energy initial. So we have the kinetic energy at point A final, which is 1/2 mv squared minus 1/2 mv naught squared, which was our initial kinetic energy at point A. And our new v is our solution to part E. So we have 1/2 mv times the square root of gme over r squared minus 1/2 mv naught squared. So that is the same as 1/2 m times gme over r minus v naught squared. And remember, r is equal to a in this case, so we're going to substitute any r's with a. So we get work is equal to 1/2 m times gme over a minus v naught squared, and that's our final answer. And for our point distribution for this part, we get 1 point for any indication that work is equal to the change in kinetic energy, and then we have 1 point for our final answer with all of the correct substitutions made. And there you go, that's the entire solution. Congratulations on solving it, and thank you so much for watching.